then, so this was kind of a depressing result. Also example in the sense, oh, it means this is not an easy problem, and that's true. And so the question was now, when you think back about chapter 2, why is this so complicated? Because the determinant is a complicated function. Also that's what you saw here. When was the determinant actually easy? Oh, the determinant was always easy if your matrix is upper triangular, lower triangular, or diagonal, which is upper and lower triangular at the same time. So for these matrices, the determinant is simple. So hopefully the characteristic equation is also simple. And that turns out to be true. So I just make it first an example, and then I just say the general case in our next theorem. So example 4. We have, let's say, a 4 by 4 matrix. And I make it as an example, I just make it upper triangular, but I can also make it lower triangular. I will not change a thing. And again, I'm not very creative. And the question are, what are the eigenvalues? Okay, so we have to solve 0 equal to PA lambda, which is again determinant of lambda times identity minus A. So this is the determinant of, again, it starts with the same thing. Lambda I means everywhere along the diagonal we have a lambda. Then everywhere else we subtract A. So -1, -2, -3, -4, 0 minus 0 is 0, -5, -6, -7, 0, 0, -8, -9, 0, 0, 0, -10. And now you see, okay, now comes again the advantage of determinant of upper or lower triangular matrix. If I calculate the determinant of an upper triangular matrix, what can I actually do? Does someone remember this from chapter 2?
Multiply the diagonals.
Yeah, you can just multiply the diagonal. Also for upper or lower triangular matrices, it's just product of the diagonal. And that's true here too. So we have lambda -1, lambda -5, lambda -8, lambda -10. And the question is, where is this equal to 0? No? And obviously, oh, if this is 0, means lambda 1 is 1. If this is 0, lambda 2 is 5. If this is 0, lambda 3 is 8. If this is 0, lambda 4 is 10. Oops, 10. So this matrix has the eigenvalues 1, 5, 8, 10. And it's just the numbers along the diagonal. And that is, and now you can imagine, I can make this matrix larger or smaller, 2 by 2, it's always the same thing. And it doesn't matter upper or lower triangular also. So the good thing is, if you have an upper triangular matrix, a lower triangular matrix, or a diagonal matrix, and someone says, find the eigenvalues by inspection, you just say, oh, it's 1, 5, 8, 10, done. Okay, so for this type of matrices, that's what I meant before. Some matrices, it's actually very easy to find eigenvalues. And these easy matrices are diagonal, upper, and lower triangular matrices. And in your book, this is theorem 5.12. So after the bad example before, this is now good news. For certain matrices, it's easy to find them. So if A is a n by n matrix, either upper triangular, lower triangular, or diagonal, then the eigenvalues are just the diagonal elements. So A11, A22, A33, up to ANN, 1, 4, 8, 10 here. So, okay, so this is kind of good. And so that is the good news. So then the next result now essentially recaptures everything we have done until now. And again, this class, like I said, is fast paced. So in some sense, I'm not really sure if this is already all clear to you, but we have already a good amount of material on eigenvectors and eigenvalues by now after about 1 hour. So this is captured now in the next theorem. What do we know by now? And then we do an example where we do the whole set. We calculate eigenvalues and eigenvectors. So first we write down what we know by now, and then we do our example. So in your book, this is theorem 5.13 and 5.14. Also 2 theorems, I just combine them in one. So theorem 5.13 and 5.14 in your book when you like to check this. So again, A n times n matrix. Then equivalent are the following statements. Number 1, or A, lambda is an eigenvalue of A. That means there is an eigenvector x not equal to 0 such that Ax equal to lambda x. So that's our definition. That will also come up here later. Lambda is a solution of the characteristic equation. Part C, there's a non-homogeneous solution, non-trivial solution to the homogeneous linear equation system lambda I minus Ax equal to 0. So lambda I minus A times x equal to 0 has a non-trivial, means not the 0, solution. And part D, that's reformulating of this. When we bring it back over, there is a x not equal to 0 such that A times x is lambda x. So this and this was actually the definition, and then this and this was come in the theorem 5.11. And it doesn't matter which one, it's always the same statement, just in different ways.
Professor?
Yeah?
What does line D say?
Lambda is a solution of PA lambda equal to 0. So it's a 0 of the characteristic equation.
I meant the last one.
Oh, the last one? There is a vector x not equal to 0 such that Ax is lambda x.
Okay, thank you.
Sorry. So there is an x not equal to 0 such that Ax is lambda x. Okay, so now we do an example. So it means first we have to find the solution of the characteristic equation. Then we solve this homogeneous system to find an x. So we do B and C, like the one in the previous page, the program I had to find all eigenvectors and eigenvalues, solve the characteristic equation first, then go and find the eigenvalues.